Yeah. Welcome, welcome.
What's your hometown in Idaho?
Rexburg. Yeah, technically Burton, but Burton isn't even a town. It's a farming community. Yeah. Yeah. It's a waste stop.
Yeah, it's the closest town. Our farm, like where our farm is located, industry. Illinois. They say it's a village of 500 friendly people.
The name of it is Industry. Dag nabbit. We earlier this week I had to teach some high school students about some history of Illinois randomly enough, and I was talking about how there was a small community named Commerce that was renamed, and I said, you know, the original name of the town was blank, you know, which is related to economic activity. I was just trying to come up with synonyms for the word commerce. And if I'd have known that there was an actual town in Illinois named, or a community in Illinois named Industry, I totally would have used it and then said, well, I learned this from one of the graduate students that this is an actual town in Illinois. I'm going to have to hurry on today's lecture because I included some slides based on the question that came up from Mylea a couple or 3 weeks ago about lighting environments and the fact that not all of the leaves get the same amount of light. And so I need to hurry and talk about it today while she's not here, so that I think she's actually giving a tour to our Thornton Chair candidate today. But we've been talking about the yield equation. I'm going to be finishing this up today, I think, and jumping into light environments just because I think they tie in an interesting way to the yield equation. Next Wednesday, I believe, is exam 2. Is that correct? Yes, it is take home. And I was visiting with Dr. Kelly. We haven't worked out the details yet, but what I'm interested in doing, and maybe we'll do this, maybe we won't, I don't know, but just keep it in the back of your head. I thought it would be interesting because we have several groups who group together for purposes of working on the instrumentation labs that we do. So I thought it would be fun. What we might be doing is polling individuals from each group and combining you in pairs with people from other groups that we will assign and say, all right, you two as a group work on this exam 2 together and, you know, work like a consulting group. So the idea would be that essentially we're forcing you to work with people that you don't get to work with every day. I thought that would be interesting, both from a standpoint of getting to know more about each other as graduate students and to be able to figure out ways to maximize, you know, the skills and capabilities that you have within those individual pairs. So, you know, we might mix things up a little bit on that. We haven't entirely decided yet, but I am looking at it being a long-term take-home, like you'll have about a week to finish it. We are potentially looking at doing it in groups of more than one. And as a result, you know, we're much more interested in what you come up with than in, you know, being able to scroll through the notes and being able to just write down what I have in the notes. So I think it'll be fun. Hopefully it won't turn into too big and long of a process for all of you. But if it does, I guess that's your problem and not my problem. But it is probably going to be a little bit more open-ended even than the last exam, which was fairly open-ended. But because it's a take-home, you know, I've had all sorts of cool stuff running through my mind in terms of things that we could test. We might even, I don't know, we might have like a math heavy option versus a math not heavy option. that's going to get kind of tricky, you know, if you're in a pair of people and one of you really likes to do math and one of you really likes to not do math. How do you decide which test you're going to take? Or do we do, like, you know, multiple questions where you have two options for each question, and, you know, you can kind of mix and match? I don't know. But as a result, I probably won't be doing like a traditional, you know, study handout, because the idea is you see the question and then you start studying and decide what you want to do for it. So be thinking of that. If you have someone in the class that you're just like, no, don't let me work with this person, email me and I'll make sure and assign you with that person. Okay. I'm kidding. But yeah. Yeah. 3, 6, 9, 12. If I get 14 emails today, turns out the class doesn't get along with each other as well as I thought they did. See, that's the challenge. Like, I personally, as a professor, feel like this is a really good class in terms of people who interact with each other well. But, you know, sometimes I oversee some of those things. As I recall last time, I think we talked about this in terms of corn, didn't we? Where essentially this green line here, which I stole this from another professor, but that's why the quality is kind of grungy. You know, it turns out when you steal a copy of a copy of a copy, it gets a little bit distorted. But yeah, this green line, this green line indicates the harvest index for corn or maize, and it's more or less a straight flat line in terms of, you know, the harvest index, and yet the grain yield has increased substantially over that same period of time. And so the main areas that we saw were, first of all, the stay green trait, and second, the canopy structure. And so when you're growing maize, if you look at biomass accumulation early in the season, it looks more or less identical between old hybrids and new hybrids. It's really after you get into anthesis and you start to get into grain filling that you really start to see the two diverge from each other. And I think, was it Kyle, did you mention that farmers complain a little bit because the crop stays green, so you don't know when the crop's ready to harvest, and so you actually have to walk out in there and, you know, check and see what's going on, which seems like a, you know, a good problem to have, but I imagine it's still kind of annoying to run into. But
How much is,
yes,
grain or corn height change over time? I remember when I worked with Tom Pioneer, it was like they really wanted like an ear height to be the same size all the time. It was largely due to lodging. So as grain yield increases, they don't want the ear to be so high up on the plant that it would cause lodging, which would then, I guess, cause harvest issues.
right. The question was, you know, how has plant height overall changed over time as well? Because it was said that, you know, they actually try to control the height of the ear on the plant to minimize lodging out in the field. I wish I had a better answer for that. I haven't actually looked into that very closely, but I will say this, you know, traditionally, especially in a crop that's already maximized your harvest index, or, you know, has approached that 50% sort of plateau for harvest index, getting a taller plant doesn't necessarily gain you anything in terms of the yield equation that I'm aware of, because, you know, you've already maximized your radiation capture because it's already a big plant. And so you see a lot of different sizes of corn that are out there, but to my knowledge, that's almost all related to what your usage is for it. So, you know, if you have a big silage corn, you know, it'll get pretty big because what you're going after is biomass. But I'm not aware that the actual height of corn has changed much, but I'll look into that and see what I can find out.
If the harvest index is staying the same, you're increasing your total yield. You have to be increasing total biomass outside of the field. So I just didn't know.
Sure.
How much of that would actually change. Is it
Right.
as for like more numbers for how many leaves come out? Instead of having
Yeah.
14 leaves,
And I would suspect that's you're going to see an increase in the overall leaf density and leaf area, but you know, height doesn't necessarily give you that unless unless there's something that you can gain by having leaves higher up in the canopy than otherwise. But that's a great question. This was an interesting study where they were looking at an older hybrid and a newer hybrid, and they've got two graphs here. This bottom one is how does the individual leaf absorption change over time, and so this top line is the increased leaf absorption, and this bottom line is the older hybrid here. And then they looked at the canopy absorption as well. So you see individual leaf absorption diverges, but then when you integrate that over the entire canopy, you see a pretty dramatic difference in terms of the canopy absorption over that same period of time. And the point that they were making in this case is, let me see if this is right here. Trying to get it to show up on the screen here. Why is it beeping at me when it's okay? I'm not going to be able to write on the screen, but the point that they make here is that the integrated difference between this line with the square dots and the line with the circular dots is directly the change in productivity of that crop, because now we've changed one aspect of our yield equation, and that integrated value in terms of that is essentially our difference in yield right there. So you can actually, if you took the difference at each stage here for these and added them all together, that's essentially the difference in your yield, which to me is pretty fascinating. So you have a greater leaf photosynthetic rate, you have greater canopy absorption, which are both tied back to the stay green technology, because greener leaves are going to absorb more radiation and you're going to have greater leaf photosynthetic rates during the same period. A lot of your differences are also related to stress tolerance, in addition to just strictly yield. And so when conditions are ideal, a lot of times some of your high producing hybrids do pretty well compared to the newer hybrids, but keeping in mind that every environment that you're in is going to introduce some level of stress, unless you're growing corn in Valdosta, Georgia, or I can't remember the other place it was, but for a long time, Valdosta, Georgia actually had the record for the highest corn yields in the world. That was recently bumped by someone else. Let's see. Anyone remember where the world record corn yields are now? Rockville, Maryland. Yeah, which is not where I normally think of in terms of, of corn, but, both Maryland and Georgia have very long growing seasons. And so if you really spoon feed your crop, you can get it to do pretty well there. Yeah, 616. The one in Valdosta, Georgia was like 567. Another thing that they've noticed is you can actually produce corn that has lower respiration rates. Now, that's useful because when we go back to radiation use efficiency right here, oops, Both photosynthesis and respiration fall into that radiation use efficiency. So one way you can improve it is bump up your photosynthetic capacity. Another way you can improve it is to decrease your respiration, which gets kind of tricky because respiration is all of the other metabolic activity in the plant. But if you're able to reduce the respiration, particularly at nighttime, you don't burn through so much carbon, and then you can use that the next day. You're never going to be able to eliminate respiration altogether because plants got to build itself. But they've pointed back to that. And then finally, so what was the main thing that we improved with wheat? Yeah, height and therefore harvest index. What were the main things that we improved with maize? Someone in the back. Really loud. I heard someone say something, but I couldn't quite hear it. Okay, radiation use efficiency through a combination of stay green, longer photosynthetic period, reduced respiration. Good. All right, so what does everyone think we're going to do with rice? So right now we've seen one example where we increase radiation capture and efficiency. We've seen one where we've reduced plant size and increased harvest index. So how are we going to do it with rice? No one look at the slide. But guess what? That's only half the story. So rice has also become a lot shorter over the last 60 or 70 years, but it's also changed in terms of radiation capture. And so rice kind of bridges between maize and wheat in that wheat is almost 100% harvest index. Corn is almost 100% radiation capture and radiation use efficiency. And rice is a combination of improved harvest index and improved capture and radiation use efficiency. So with rice, changes in canopy architecture have had a big positive impact on yield. And your higher yielding rice genotypes have more upright leaf angles. So interestingly enough, and I'll actually show you some examples of this, assuming I get to it in this lecture today, but I'm going to describe how leaf angle in a high sunlight environment can dramatically improve your photosynthetic possibilities with rice. But back in the 1950s, one of the highest yielding cultivars was Nanjing 6, and it had a leaf angle of 10. When I say leaf angle, I have got to figure out how to get this to work, or else I'm going to be really disappointed here. Because if I write on the board, everyone online can't see what I'm.
What if you do the thing on the side? The projector.
Okay. Maybe. And a pen. All right. Apparently Dr. Ritchie doesn't come to class prepared.
Well, when you're the head of
Yeah, yeah. That's right. When you're a department chair, you can't be expected to actually use your brain. Yeah. Sure. Yeah, I'll try it with the pen. I don't want it to bleed over and have to explain to Robbie what happened. So here's our plant. Here's the plant leaf. If the leaf is completely vertical and upright, this is going to be 90 degrees. If it's completely horizontal, it's going to be 0 degrees. So 10 degrees looks about like this, or even a little bit less. And that's what the cultivars looked like back in the 1950s. Now, by the 1970s and 80s, the average leaf angle on some of their highest yielding cultivars was 82 degrees, which was almost vertical leaves on these cultivars. Thank you. I'm not a very good writer when I'm trying to do that, but we have dramatically changed the leaf angle that we expect to get with our rice cultivars. And it hasn't just been one day we started doing it and we went from 10 to 82 degrees. You know, in the 1960s, we were in the 50s, the 1970s we were in the 60s and 70s, and we've been gradually increasing that leaf angle up to a maximum level where in a high sunlight environment, we can maximize yield, but we've reached a point where you can't go more than about 80 or 82 degrees before you start running into other problems, which I'll try to show you in a little bit. And so what you see as we've increased the leaf angle and made more upright rice plants, you actually see it becomes a lot more of value to the plant as you increase your light intensity. So at a low light intensity, oh, now my mouse isn't even showing here. But at a low light intensity, like right here, you don't really see a lot of advantage in the plants, but at a high light intensity, you see a nice separation between the old cultivar, which is the dark black circles, and the new cultivar, which is the white circles. And it's not just that you're absorbing more light potentially, it's also that your leaf area index is allowed to increase, so you've got more tissue that you're able to pump back into the plant in order to make yield. So we talk about, did I talk about average leaf area indices for different crops? So just to give you kind of a layout, a big robust cotton crop is going to have a leaf area index of about 3 or 4 meters squared per meter squared of ground area. I've seen some of them up as high as maybe 4.5. Really, if you hit that high on a cotton crop, you've usually kind of overshot the mark in terms of your irrigation and your fertilizer. With corn, it's not uncommon at all to have leaf area indices of 6 or 7 or 8. What they found with rice was, optimal leaf area index back in the 50s was maybe about 6, but over time, this optimal leaf area index has increased to where, now you have rice cultivars that have leaf area indices as much as 10 or more. And so you've got a massive quantity of plants that are out there. They cover over the ground more quickly, and they've got massive stacking of their leaves to absorb radiation. Now, yes?
The higher leaf area is the reason why they were blocking the resistance.
Oh, okay. And it was brought up that the higher leaf area index was also another reason that these rice cultivars are more lodging resistant as well. That's a great point, and I'm glad that you bring that up. And my understanding, am I correct in my understanding that it was both an increased number of leaves and also shorter stems as well? So, rice really worked toward several advantages, more so like with wheat, it was primarily lodging resistance and increased harvest index by making the plant shorter. With corn, it was primarily radiation capture and radiation use efficiency. And with rice, it's a combination of, and that's a good point. If your plant's lodging, you lose any advantages that you have through any other mechanism of increasing yield. But shorter plants, more leaves, more radiation capture, more lodging resistance, and higher yields as a result. So I summarized this just to say that pretty much that. The wheat's harvest index, corn has primarily been radiation capture and radiation use efficiency, and rice has been radiation capture and harvest index. I thought it would be interesting, since I knew this lecture was kind of coming to an end. I thought, you know, where do we want to go next? And I thought it would be interesting to jump into the concept of, you know, what does a plant look like in different light environments? What do leaves look like? Because it turns out that a leaf that does really well in a high light environment is not the same leaf that does really well in a low light environment. So I thought we would play around with that a little bit and see how we can do it. So to get into this, photosynthetic efficiency can be talked about in a lot of different ways. I think we mentioned, you know, the biochemical level has a maximum photosynthetic efficiency that you can expect of, you know, maybe about 17% on an energy basis efficiency. But when you get into a crop scale, we actually, and this was something that I knew from a standpoint of being in class, but it was interesting to see as we were actually doing the numbers. When I first came here, we were doing some research on irrigation timing in cotton. And one of my graduate students, Fulvio Simo, was doing a project where he was using a Lycor photosynthesis system to measure leaf photosynthetic rate out in our cotton plants. And as you stress the cotton crop, the leaf photosynthetic efficiency and the water use efficiency actually improved compared to when you were given the plant plenty of water. So if you were looking at it on just a leaf basis, if you tracked photosynthetic efficiency and water use efficiency over the course of the season, these stressed plants were doing really well. In fact, they were much more efficient than the same leaves on water, you know, sufficient plants. And yet, when you actually looked at the yield versus the quantity of water that we put on throughout the season, the water use efficiency and the photosynthetic efficiency were actually dramatically reduced in comparison to our control plants for most of our irrigation treatments. So why is that? How can you be taking measurements on a weekly basis and your measurements show that your plant is being very effective at photosynthesizing, and yet at the end of the season your plants did really terrible in terms of the amount of water versus the amount of yield? All right, one idea is vegetative growth versus reproductive growth. Good idea. Other ideas, and just throw some ideas out. I'm interested in how would y'all get to the bottom of this? Riley, what do you think? What's that? Okay, the respiration could certainly be high, especially if the plant's heated up more. The respiration is certainly going to increase. Other ideas? Going back to our yield equation. What's that? Right, for fertilizer efficiency. Yeah, and again, you know, the plants had plenty of fertilizer for the growth that they had. Darn it, now I've got to wonder, should I tell you what we discovered, or should I put that on the test next week and have you kind of sleuth it out? Yeah, both. Both. I like that. Yeah. Maybe we'll have some interesting question that's related to that. But essentially, what we found was similar to what was being described. And also, we were very efficient on a leaf tissue basis in terms of what the plants were doing, but the leaf area was dramatically decreased over this period of time because even though the plant was efficient, it wasn't being productive. And those decreased leaves in size then had reduced radiation capture. And as a result, they had reduced, carbon supply. And so it was this cascading effect. And so, then for the big finale, the harvest index at the end of the season was poor. And so, we helped one little fraction of this yield equation, and we penalized on every other part of the yield equation. They also didn't grow over as long of a season before they matured. And so we decreased radiation absorption. We increased a portion of the radiation use efficiency, but we harmed other parts of the radiation use efficiency. We harmed the amount of time that we had, and we harmed our harvest index. And so as a result, the actual yield that we got per unit of water that those plants received was very poor compared to just irrigating the cotton with all the water that we wanted. And what we found, and this was 2011 and 2012, which were very dry years, what we found was if you had a set amount of water that you could use during the season, you could yield better on an entire field by not planting anything on 75% of the field and irrigating the other 25% fully than you could by trying to put water on everything all the time. So, it's a dividing of resources here. So with photosynthetic efficiency, and again, this is a summary of a lot of details that go into this, but you've got two processes. You've got the light dependent processes, which you produce ATP and NADPH. And then you have the Calvin cycle or the carbon cycle, where you use this ATP and NADPH to make carbohydrates out of carbon dioxide. This is worth mentioning. I'm not sure whether I talked about this or not, because I'm getting old and forgetting a lot of things. But remember how I said that plants can be about 17% efficient for photosynthesis? This just talks about how do we get that 17% efficiency, and what's our maximum theoretical efficiency that we could have. You remember we were talking about how you've got blue light that's absorbed by plants, you've got some green light, you've got red light that's absorbed by plants. It doesn't matter whether you have a red photon or a blue photon coming in terms of the plant being able to use it for photosynthesis. Obviously, color has other effects on a plant, but a plant can be just as useful with a red photon as a blue photon, even though it has less energy. And so if you take the lowest energy light that you can use, which is red light, and if you perfectly convert that into carbohydrate, which I have shorthanded here as CH2O, you couldn't do it with one electron. It takes 3 electrons to run the process. So right off the bat, your maximum quantum efficiency is just going to be 1 mole of carbon dioxide per 3 moles of photons. And the challenge with that is a mole of carbohydrate contains 468 kilojoules of energy that's been added, and 3 moles of red photons contain 525 kilojoules of energy. So you've already lost 11% of your energy just by that conversion, because you can make 468 kilojoules of CH2O, but you used 525. So you've already lost 10, 11% right off the bat before we've even gotten into the fact that the plant isn't going to be 100% efficient. The next thing you run into is that assumes that every single photon is going to be hitting a chlorophyll molecule, and not something else? Well, there's a lot of stuff that you can be hitting in a plant that is not chlorophyll molecules. It could be cell walls, it could be cytoplasm, it could be a lot of things that aren't strictly chlorophyll. And so if you hit anything other than a chlorophyll molecule, or if you hit a chlorophyll molecule that's still running the previous reaction from the previous photon that hit it, it's not going to have a chance to turn this new photon into carbohydrates. Rather, it's just going to turn it into heat. And so after you factor that in, the quantum requirement becomes about 8 moles of photons per mole of carbohydrate, which comes out to about 33% efficiency. So we're already down to, you know, we went from a free throw percentage here, 89%, to now we're at a batting average about 33%. Yeah, we went from Stephen Curry free throw to Shaquille O'Neal free throw just through that step right there. So did you realize that the best plants can do in photosynthesis is at the absolute theoretical maximum is only 33% efficiency? That's pretty terrible, isn't it? How many of you say that's pretty terrible? That's okay, you can admit it. Plants are terrible. One of the things I thought was interesting as I was putting this together was I looked at what's the theoretical maximum efficiency that we could get if instead of using plants, we were using solar cells. And, you know, the solar cell that you get like in a calculator is only like 3% efficient, but you can get high quality solar cells that are extraordinarily efficient. But the maximum solar efficiency that you could get with a solar cell, and this is a theoretical value, this isn't what they're actually getting, came out to about 35%. So plants do pretty well. And you're still going to have respiration that goes on. So after you factor in the fact that you're only getting 89% efficiency conversion of photons to electrons, to carbohydrates, and you're losing a bunch to the fact that photons are hitting stuff other than chlorophyll, and the fact that the plant has to respire, your maximum energy efficiency is about 17.7%. Bless you. And then, you know, in practice, that actual maximum efficiency is dropped even a little bit below there. Now, if you have a high light leaf, the amount of photosynthesis you can do is going to increase with the amount of light that you shine on it up to a limit, and that limit is pretty high. How much light do we get on a sunny day in Texas? A lot, yeah. If we're talking about micromoles per meter squared per second, we're at about 2,000 micromoles per meter squared per second near solar noon on a hot sunny day, which comes out to about 435 watts per meter squared of photosynthetically active radiation. So quantity is moles, energy is watts, but you know, we're looking at about 400 plus watts per day or per second. Sorry, let me back that up. A watt is a joule per second. We're looking at about 435 watts per meter squared, which is 435 joules per meter squared per second, every second that the sun's out during the middle of the day. And that is a little bit above a saturation point, even for a leaf that's accustomed to direct sunlight, because at that point, you know, the average that you're going to get over the entire day is going to be more like about 200 to 250 watts. So these leaves are actually acclimated to try to maximize their photosynthesis when you hit about 200 to 250 watts, because you know, the rest of the time you're giving up something just to increase the responsivity. So a sunlit leaf is going to have a period of time where your photosynthetic rate is going to increase in a straight line with your amount of light that you're getting. And eventually it's going to reach a point where the amount of additional light that you get starts to have less of an effect on photosynthesis, because at some point during this period where it's a straight line right here, light is the primary limiting factor in terms of your increased photosynthetic rate. But at some point, light is no longer the limiting factor in terms of your increasing photosynthetic rate. The ability of your chloroplasts and your chlorophyll and the other mechanisms within your chloroplast are the limiting factors, because you just can't keep up with the amount of radiation that you're getting. Wish I included the video on here, but I actually have a video that I found where it shows in a low light situation. There's a plant and it shows, I think it's Elodea, but it's a single layer plant leaf. Shows it during a darker period of time, the chloroplasts actually spread out to try to maximize their absorption of light. And then as it gets brighter and brighter, all of the chloroplasts push their way out to the outside of the cell to where they're just kind of packed together to try to minimize the amount that they're each absorbing, because, you know, sunlight can actually cause a lot of damage to them as well. So they actually have two different strategies. Let me see if I can real quick. Let's see. All right. So this is a low light situation. You see they're spread apart pretty well. What are all these bubbles going on here? You see these little bubbles around the outside of the chloroplast? What are those? like the little tiny bubbles around the outside of these chloroplasts. Yeah, those are actually indications that you've got metabolic processes going on, and they're actually a result of the respiration that's occurring in there. So yeah, so they're like little air pockets. Kind of cool, huh? In this case, I would say it's mostly oxygen, but you're probably also getting a little bit of carbon dioxide. It's unlikely that you're heavily seeing carbon dioxide in this case, because with a chloroplast, the primary metabolic function is photosynthesis, which starts out with the very first step on photosystem 2 and photosynthesis is the splitting of what into what? Water into, sorry, the very first step of the light reactions in photosynthesis, you're splitting water into two constituent molecules, which are hydrogen and oxygen. And so your net production in the chloroplasts is oxygen. And so I suspect that this is primarily oxygen that's coming out of these. Prove me wrong. Let's see. Okay, so nighttime. Let's see if they have a daytime. Oh, I'm going to be disappointed if they don't have a daytime. Yeah. Darn it. I was totally going to use that nighttime. Here's a daytime representation. See how they're all right around the outer rim of the cells. All right. Yeah. Yeah, you can do some cool things with a microscope as long as you're willing to torture enough plants to do it. Oh, I shouldn't tell you this because we only have 5 minutes in class and I still want to talk about some other stuff, but which weighs more, a ton of lead or a ton of feathers?
Equal, because they're a ton.
You'd think. However, with a ton of feathers, you also have to deal with the weight of what you did to all of those poor birds. All right. Yeah. Yeah, my son told that to me when he was in high school. I'm not going to get into the PRI curve equation right now, except to say that it's set up. Oh, interestingly enough, does this actually start at 0 and 0 here? Okay, so it starts at 0 irradiance and what for a photosynthetic rate? Theoretically, and not just theoretically, but in actuality. Can you get a negative photosynthetic rate according to this graph? So what the heck? Sorry, I don't know if I'm allowed to use heck in here. How is it possible that we're getting negative photosynthesis going on? Help me out, someone who does gas exchange work. What's that? Respiration, exactly. It turns out that if you turn all the lights off, the plant is going to, instead of consuming carbon dioxide, is going to be producing carbon dioxide through respiration. And so this negative value of photosynthesis is actually a negative net photosynthetic rate because you've got respiration going on with no corresponding photosynthetic rate. So the equation for the PRI curve is simply this, that if you take the amount of light that you have, if your light is 0, your entire net photosynthesis is going to be your dark respiration right here. And let me see if I have that in here. This is a couple of more steps deep into the process here. So this doesn't strictly show that one, but I think it's worth showing you this just for purposes of the class. We'll end on this. So if we've got a sunlight, micromoles per meter squared per second, blah, blah, blah. If you have a sunlit leaf versus a shaded leaf, these are going to look very different. So let's do sunlit here, shaded here. All right, what's the minimum amount of sunlight that we could have at any given moment? 0. Yeah. Yeah, I mean, let's imagine we're in a deep dark cave here. Yeah. Actually, let me do it in tens just because I don't want to take forever dragging down here. And what did I say kind of a top end would be? 2000, yep. All right. So let's say respiration, and then this is going to be slope, which is this, is this a theta here or phi? Phi, okay, phi, and then A max. All right, a shaded leaf's goal is to minimize the amount of energy that it's using. So it's generally gonna have a relatively small respiration, whereas a sunlit leaf is gonna have a really high respiration. I won't go into this right now, but your slope for a sunlit leaf is going to be lower than it is for a shaded leaf. And your maximum photosynthetic rate can be quite a bit higher for a sunlit leaf than it is for a shaded leaf. So I'm going to go super high and quite a bit lower here. Now, if I put this equation in, this is our sunlight, which is the ppfd, times my slope, times my maximum, divided by PPFD again, times my slope, plus my maximum. What mistake did I just make there? That's right. Okay, minus my dark respiration. Let me just do the same thing here. Oh, it's 950. You're never going to know the answer. Let me show you real quick just on this one. When we draw this out, you can reach a very high value here, but if you're at a low light level, like early in the morning or in the middle of the night, you're going to also be losing a lot of carbon during that period of time as well. With a shaded leaf, you don't get nearly as high, but you don't lose nearly as much carbon down here too. So a plant produces both sunlit leaves and shaded leaves to maximize things when you've got a lot of light and to minimize losses when you don't have a lot of light. Everyone have a great day, and I'll look forward to talking to you on Friday. Remind me that this is kind of where we ended up on Friday.